And now I'm going to speak about some symbolic dynamics in Kuramoto-Sivashinsky PDE, one-dimensional Kuramoto-Sivashinsky PDE. This is joint work with Piotr Wilczak. I would like to present you some recent results regarding this system. And on this slide, I have some meta scheme for computer-assisted proving dynamics. Usually we have some theory that allows us to reduce the problem in dynamics to some finite number of inequalities usually. And then we need some algorithms that compute quantities that can be then changed if they satisfy those inequalities. And then if we are lucky, we can apply this to some particular systems. And I would like to reverse a little bit this order. So I would like to start from the main results. Then I would like to present some theory. And then it will be clear what kind of tools do we need for those computations. At the end, I would like to present the most technical part of these results. And I would like to switch to algorithms for rigorous C0 and C1 integration of PDEs. So let me start from the result. Kuramoto-Sivashinsky, we consider one-dimensional Kuramoto-Sivashinsky equation with 2 pi periodic and odd boundary conditions, and this leads to some infinite dimensional ODE for Fourier coefficients of these solutions. And this system is written right here, over here. And the main property of the system is that if you look at the linear part, so we see that with k going to infinity, this linear part is strongly damping. So the system is dissipative. And this is the main result of this particular infinite dimensional ODE. So for the particular choice of parameter value 0.1212, there is an invariant set H, which consists of countable infinity of periodic orbits of arbitrary large principal periods. Moreover, there is chaos in the sense of the presence of symbolic dynamics. Of course, symbolic dynamics is discrete systems, so some certain Poincare map admits symbolic dynamics. And this is a result already published this year in Journal of Differential Equation. And the second theorem is a very hot result, just 2 weeks ago, perhaps I got it. So in this set H, there is a selected periodic solution A1, and there is countable infinity of homoclinic orbits to this periodic orbit A1. Let me show you the geometry of those orbits. So if we choose a Poincare section for this system A1 equal to 0 and say crossing direction is negative, and we consider Poincare map on this section, we can observe chaotic attractor. So this is just from the simulation what you see below. On this attractor, we see one fixed point marked here by blue dot, and period 2 orbit marked here by 2 red dots. And here are profiles of these orbits. Well, actually not profiles. This is evolution in time of the profile of the blue orbit and the red orbit. So we see that here is the 2 pi domain, and here is period of the orbit, which is almost very close to pi actually. And this is period 2 orbit, so we see that this is double period up to 6 something. Okay, so we see evolution in time of the profile of those two solutions. And on this attractor, which is on the Poincare section, we have found some approximate heteroclinic orbits between A1 and periodic orbit A2, and in opposite direction. So we see that at the beginning, this heteroclinic sequence here is very close to A1 and then follows some points on the attractor. And actually the point denoted here by A9 is very close to already red dot, and the same in the opposite direction. So given this approximate heteroclinic chains, we are able to construct some shadowing trajectories. In this sense, we have symbolic dynamics. So the result is the following. If we have any path on this graph, a B-infinite path, it corresponds to a trajectory of the system. That means that if we have the infinite path of symbols, blue and red, then we can try to find trajectory which follows this code of symbols. That means that the solution goes very close to the blue orbit, then to the red orbit, and can stay for a while next to the red orbit, etc. If we choose a periodic path on this graph, then we can find periodic solution to the original system. And if we choose homoclinic path to the blue dot, so every homoclinic path to the blue dot corresponds to homoclinic solution to the blue orbit. Okay, so we see that there is a countable infinity of homoclinic orbits, and they have different shape. Okay, so this is the result. And now I would like to mention some previous results about this system. If mu is large, then the constant solution is globally attracting. For mu equal to 0.75, it was a computer-assisted proof of the existence of non-trivial equilibria by Wilczak and Mishaikov. And then there were some proofs of the existence of some symmetric, some of them were symmetric, some of them not, periodic orbits by Wilczak also. And I would like to mention a paper by Arioli and Koch from SIATS 2010. They gave a computer-assisted proof of the existence of hyperbolic periodic solution, and they computed also the spectrum of these Fokker multipliers of the orbit. Some other results also regarding periodic solutions for different parameter values, and we have now those two results that I guess follow the previous results in this for this system. Okay, so now I would like to switch to the theory. What kind of proofs do we need for those proofs? The proof consists of, well, we have two theorems. One of them is topological, second requires some C1 conditions. For to obtain symbolic dynamics, we are using so-called covariant relations, but this method is adapted now to infinite dimension. So it was known for finite dimensional system for many years. The theory goes back to Easton and his paper in Journal of Differential Equations from 1975. And then in pure topological setting, it was proposed by Wilczak in 1997 for two-dimensional maps, and then extended to finite dimensional maps in any dimension but finite by Gidea and Wilczak. And now we propose a version for compact maps in infinite dimension. So we would like to apply this method to Poincare maps for the system. And to obtain homoclinic orbits, we need C1-like tools. We need some arguments for convergence. And for this purpose, we adopt C1 conditions known also for finite dimensional system to these infinite dimensional settings. Let me start from the first part now. I'm going to recall this method, but this method will be given for infinite dimensional setting, and I'm going to mention the differences between this finite dimensional version and the version for infinite dimensional maps. So I'm going to define some geometric object. We assume that everything is in some real normed space, X, and we call a triple N an H set if N is a compact subset of this domain, say X. U is a non-negative integer. So this is a number which stands for a number of expanding directions in our set. And we have also a homeomorphism which maps our set N to a product of something which is U-dimensional closed ball and something which is convex. Okay? And the difference between this infinite dimensional version and finite dimensional version is that in finite dimensional version here was a ball also. Of course, ball is convex, but in infinite dimension we cannot speak about the interior of sets because usually we play with compact sets which have empty interior. So this is why we are choosing only this assumption that we have convex set here. So below we can see the geometry of the situation. Here we have some Tn, which is convex and contains, for instance, 0. And here we have a ball, and this is a product of those two sets, and the homeomorphism, which maps this into some shape in X. Okay, so this is geometric object in our phase space. And then we have to play with dynamics. So assume that we have two H sets and an M, and they have the same unstable dimension. U of n is equal to U of m, and we assume that we have a continuous map which maps, which is defined on the set n and with the range in Y. And given this map F, we define also F subscript C, map, which is just F, but expressed in the coordinate systems of the set N and set M. And here is a definition of covariant relations. So this is something which connects the geometry of set with the map which acts on those sets. So we assume that, we say that F covers M if there is a linear map, which is isomorphism actually, the U-dimensional map, and there is a compact homotopy which deforms this mapping FC to a linear map and 0 on the tail. So maybe the geometry is better to present here. So we have this NC, this is the set which is given in the proper coordinate system, and we have a map FC, which maps our set NC to some space Y, and we can deform this mapping FC to some linear map L and 0 on the tail, which can be infinite dimensional. But what is the main difference between finite dimensional version and infinite dimensional version? For finite dimensional version, here is this geometry of this definition. We assumed that the range, during the homotopy, we cannot touch these blue lines. So the range is mapped. So the range of the mapping F cannot, well, image of NC by the mapping FC cannot touch those two blue lines. In infinite dimension, we cannot say about the interior of the set. So we assume that we have to stay in the strip. We can touch the boundary here, but we have to live in the strip. Okay? So this is the major difference. This infinite dimensional version also applies to finite dimensional as well. Okay, so we have geometry, we have a mapping defined on some edge sets, and we have the definition of covariant relation. And this is the main theorem, which says that if we have a sequence of covariant relations from N1 to N1, and we can follow some intermediate sets, then there is a trajectory that follows those sets also, and this is a periodic trajectory. So we can start and end at the same point. And the proof rely on Lereshauder fixed point index for compact maps in convex spaces. Okay, so this homotopy allows us to define for each covariant relation, we have a homotopy. From those homotopies, we can build a homotopy between some extended map in extended phase space and show that it is homotopic to a linear map which has proper index. And this index is non-zero, then from this we conclude the existence of periodic solution. And here is the crucial point, because this set U, which is equal to open ball times Tn, is open in Ru times the same set Tn. So we cannot speak about the interior of the set because it is empty, but we can say about relatively open sets. And this is the primary tool for proving the existence of shadowing orbit, periodic orbit, etc. And from this theorem, we have nice corollary, which says that if we have some pairwise disjoint sets, and we have a set of symbolic admissible sequences of coverings, Then there is a projection from the invariant set H, which exists, and to the space of sequences, such that every sequence from sigma corresponds to a trajectory of F, and periodic sequences correspond to periodic orbits for the mapping F. So this is a theorem which is known for finite dimensional version, exactly the same we have for infinite dimensional mappings under slightly modified definitions. Okay, so here is a method for proving the existence of symbolic dynamics. If we can construct two sequences of covariant relations, we start from some, say, periodic orbit blue here and a periodic orbit red, and we can transport, well, we can find a sequence of covariant relations joining M0 with M0, and the same in the opposite direction. Then we have something, then we have symbolic dynamics for our system. So this is exactly what we did. We constructed a sequence of covariant relations in both directions between those two periodic orbits, fixed point and period 2 point for Poincare map. And on this slide, I would like to show you how we can validate the existence of covariant relation for a given system. So I assume that my sets will be a subset of L2. And I will represent subsets of L2 in the following form. To describe the point, I need a finite dimensional vector an, some matrix, some positive integer as some real number, and also some real number C here. And my set is just parallelepiped on the main coordinates. This is described by first two line, and uniform bound for the tail. So one quantity here and one quantity here describe the tail. So this is just set of geometry decaying sequences. Okay, and H set in coordinates of H set, my mapping is defined on the n-dimensional ball -1 to 1 to the power n times some tail. And if I'm going to validate the existence of covariant relations for in particular map, I have to check some inequalities. First of all, I have to check these inequalities. That means that the range of the image of my set NC should be contained in this set. That means that I have to check actually n-1 inequalities for those coordinates. Okay. So absolute values of them should be less than 1, less or equal. And the range, the image of NC should be also contained in TM. That means that I have to compare only the constants if I assume that they have the same Q. So this is really finite number of inequalities. Second condition is either or. So in one-dimensional case, the image of, oh, sorry, here should be one cross only. The image of -1 times this should be positive, first coordinate of this, and the second projection should be negative or vice versa. So that means that this should be negative and this should be positive. So I have a really finite number of inequalities that have to be checked, and in this way I can verify that some set covers the other set by mapping F. In the context of Kuramoto-Sivashinsky PDE, I'm going to apply this to Poincare map of the system. So I need a tool for computation of Poincare map. And this will be our algorithm for rigorous integration forward in time of some class of dissipative systems. Okay. Now I would like to switch to C1 tools for obtaining homoclinic orbits. This is just straightforward adaptation of conditions to infinite dimensional settings. So if I have some H set n, I can define quadratic form in this form. Here X is finite dimensional, usually U dimensional. No, yes, and Y can be infinite dimensional. And I say that NF covers N with condition if the following inequality holds true. for every u and u1, u2 from the set n, both different, well, different. And if this holds true, then the mapping F has unique fixed point in the set n. And also we have the property that every full forward trajectory in n must converge to this unique fixed point, and the same happens for backward time. And the proof is pretty easy, more or less. The existence of fixed point follows from covariance relations, okay? The uniqueness, so assume that we have two of them, different, and then, of course, because they are fixed points, we have the first equality, and by the property of condition, this has to be greater than this quantity, so we have contradiction. So we have only two fixed points, well, one fixed point in the set, and we have also convergence property. We can find a constant d, which is an upper bound for the value of quadratic form on the set n here. Sorry for my mistake, should be n. Why? Because this is a compact set. And if we have a full trajectory, full forward trajectory of, say, point v in our set, then we have this sequence of inequalities, which is bounded from above by the constant d. So this is just standard layout point of function argument that this has to converge to a fixed point. Well, but how we can validate this inequality? Okay, how we can validate this inequality for every u1, u2 different. Sorry, one more slide. This tool allows us to prove homoclinic orbits. Of course, if we have a sequence of covariant relations, which is non-constant, and it is homoclinic to n0, and we have conditions on n0, then of course, forward trajectories have to converge to blue, and backward trajectories have to converge to blue, so we have homoclinic orbit. So how we can validate conditions? We have to compute the difference f of u1 minus f of u2, and using integral form, we have this equality. The matrix A is given by this integral. If our mapping F has continuous partial derivatives, and our inequality for quadratic form is simply transformed to positive definiteness of this interval matrix A. Okay, here we have a convex hull of all derivatives at points from the set N. So again, in order to check conditions, we need to compute derivative of our mapping, compute some matrix, and show it is positive definite. So again, we need an algorithm for computation of derivative of Poincare map. Good. I'm going to switch to the most technical part. Sorry for that. To the best of my knowledge, there are several algorithms for integration of dissipative PDEs, and C0 algorithms are, I'm not sure if this list is complete, perhaps not. But there are some algorithms. I'm going to present now our approach from this paper in 2020. And to the best of my knowledge, there are only two algorithms, one published. First is by Arioli and Koch from 2010. And now we would like to present slightly different approach to integration of variational equations. I'm going to start with this C0 integration. The algorithm consists of several steps. First, we have to check that the solutions exist over a time step. So for this purpose, we need some hybrid high-order enclosure and dissipative enclosure. We are using here, heavily we are using this dissipation of the system. The method is based on Taylor method or Hermite-Breshkov method, which is implicit, but both rely on computation of Taylor coefficients of the solutions. So we designed, we proposed some algorithm for automatic differentiation of PDEs, well, solutions to PDEs. And given this Taylor coefficient, we can define explicit Taylor method or implicit Hermite-Obreshkov method. And I would like also to emphasize that this Hermite-Obreshkov method has very small remainder in comparison to Taylor method. This is the scaling factor. So if the Taylor method is of order 20, that means that the Hermite-Obreshkov method has the remainder the same as Taylor, but divided by 20 by 10. So this is just like 1 million, for instance. And of course, we also need some algorithm for computation of Poincare map in proper coordinate systems. And this is implemented in our library, but I'm not going to speak about this. This is too technical, and I have no time, I guess, for this. I'm going to recall the algorithm for computations of enclosure for ODEs, finite dimensional ODEs, because I will be building on it. So assume that we have some finite dimensional ODE, and we have a set of initial conditions and some time step we are going to make. And if we can find Y, which satisfies this inequality, that means that x plus 0 times the interval from 0 to h times vector field evaluated on Y, and this should be interval whole of this. Well, no, because we have interval here. So if this inclusion holds true, then the solutions for our ODE exist for this time range and for any x from the set capital X, and moreover, they belong to Y. So this is very easy, straightforward way to find some rough enclosure for our system. And here is an example how it works. Consider this very easy planar, planar system, and we can set this particular time step, and our red set is our set of initial conditions, and then we guess set Y as our candidate for rough enclosure. We evaluate here vector field on the same set X, but here we a little bit enlarge our time step. Okay, it should be 0 to H, but it is minus 0.2 to 1.5. So it is a little bit larger. And this is our candidate for enclosure, and then we check inclusion. Okay, so we can compute this quantity, and it is contained in Y. So this is how it works for finite dimensional systems. Of course, this is the worst method for finding an enclosure. We have also higher order enclosure methods that performs better. Okay, so I'm going to switch now to infinite dimensional settings. So we have a vector field, which is defined on some subset of L2Q. By L2Q, I mean the subset of L2, which consists of this geometrically decaying sequences with constant Q. And we have vector field, which splits into linear part, which is strongly damping, and this nonlinear part. And our standing assumptions are the following. The assumption C1 says that the linear part, this constant here, behaves like k to the power p. Okay, and it is because of the sign here, it is negative. The second condition says that the nonlinear part can be bounded on any compact set by some constant which depends on this set. Here we have the same geometric decay. It may happen that we have k to the power r here, but this r is less than p. Okay, where p is the growth of eigenvalues. Okay, more or less. The C3 to C5 are technical. I mean, Fk, component-wise, it should be continuous. It happens, okay, quite often. The second condition is about some inequality regarding the logarithmic norm. This allows us to force some convergence argument. And the C5 condition says that nonlinear part is all partial derivatives are continuous. In Kuramoto-Sivashinsky, this is just the polynomial, so they are continuous. So there is no problem with this condition. The most important assumptions are C1 and C2. They gave us dissipation, okay? The last three conditions are technical. And our algorithm works in these settings, okay? And here we have a little lemma which shows that under those assumptions, we can always find a rough enclosure for a PDE, okay? So if we have a compact set and then there is a time step which is unknown, but it is, and there is an enclosure for this system with this set H. And the proof is quite easy. We can always take B, which is just a set of geometry decaying sequences with the constant S, and we define enclosure in the same form, but with the constant twice larger here. And the nonlinear part can be bounded because of assumption with k to the power r times constant, and here is geometric decaying constant also. And from the first two conditions, we can compute inner product. Well, we can compute, we can show that for k sufficiently large, the vector field is pointing inwards our enclosure, candidate for enclosure, because of C1 and C2. That is, if we compute this quantity, then we end up with this inequality to be satisfied. And we see here that this is positive, of course, and here is a constant, but here we have positive quantity times k to the power, sorry, negative quantity times k to the power p minus r. And here is the place when this inequality is very important, okay? Because it is positive, then of course this quantity goes to minus infinity, so this can be negative. And it is negative for k large enough, okay? So for k large enough, we have this property that vector field is pointing inwards on the modes. And then on the finite number of modes, we can shorten the time steps such that we have inclusion, okay? And that's it. So this is a pure theoretical result, completely useless in practice, but it shows that we can integrate always, okay? In practice, we use higher order enclosure method. So this is finite dimensional version. If we can find an H set Y, well, not H set Y such that this inequality, this inclusion holds true, then Y is an enclosure for our system. And we can also bound solutions by this expression here. Of course, we need a good automatic prediction of time step to make this remainder as small as possible. Okay, how it works in infinite dimension? We adopt this structure, this method to infinite dimensional settings. We have some parameters of our algorithm. First of all, we have some order of enclosure, and well, it is usually not that large as I would like to have. For ODEs, we have 20, 25, 50, whatever, almost. But for PDEs, it is 3, 4, 5. Okay, I would like to have larger. We have also some constant d, which is positive integer, and it stands for the number of modes in our L2 sequence on which we apply high order enclosure. And we have a candidate for time step H0. And then what we do? First of all, we try to find some candidate for enclosure on the main modes for the time step H0. This is as for ODEs in finite dimension we do. Then we try to enlarge a little bit the tail so that we have inclusion on this tail, okay? Because of the dissipation, if D is large enough, of course it is known and fixed, but probably we can enlarge this tail so that we have inclusion. And then we come back to the main modes and we validate that we have enclosure on the main modes. So on the tail we have enclosure because the vector field is pointing inwards, and on the main modes we just check inclusion using higher order enclosure approach. Sometimes we need to adjust time step, shorten it a little bit if we have no inclusion. Why? Because a recomputation of Taylor coefficients, etc., is very costly. So it's sometimes better to shorten a little bit time step than recompute everything again. And usually we have the following strategy. We have user-specified tolerance per one step. So this is the error which is acceptable by the user. And our enclosure is component-wise in this form, okay? So yk, kth component of enclosure is Taylor polynomial plus minus epsilon epsilon, which is this tolerance. And then our enclosure is a set which I call in my code geometric bound, which is in this form. We have some number of intervals here and two quantities, constant and q, which correspond to this geometric decay. And we compute some trial enclosure on the main modes, and then we enlarge this constant c on the tail so that we have this inclusion. And it is possible because the linear part is bounded by this, should be p here, sorry. And the nonlinear part is bounded by this, and p is greater than r. Well, it is correct, but it doesn't fit the previous slides, okay? But because of this, we have this inclusion. And then we compute Taylor coefficients on the main modes. We check the inclusion. And if it is not satisfied, then we shorten a little bit time step so that it is satisfied. Okay, so this is what I would like to say, that it is very costly to recompute Taylor coefficients, so it is much more, it's better actually to shorten a little bit time step. And it is possible to find H because the tolerance is symmetric around 0. So we always can shorten time steps such that this inclusion holds true. Good, and here's a picture. If we have our initial condition, first we predict enclosure on the finite number of modes, then we enlarge a little bit on the tail to have isolation, and then we come back to the main nodes and shorten a little bit time step. So this is C0 algorithm. Given enclosure, we can compute trajectory after time step h using Taylor method or Hermite-Dobreshkov method on the main nodes. And here is our numerical scheme. For instance, this can be a Taylor method. And we also have to split initial condition into two parts. This is the main part, which corresponds to the coefficients we are describing explicitly. And here is a tail, which is given just by two numbers, C and Q. And on the main nodes, we use the mean value form to enclose numerical method, actually. And at the end, we have to add the remainder to this. And on the tail, we are using differential linear inequality, because we have the property that the vector field is pointing inwards on the boundary, then we can bound the solutions by this, the solutions to this inequality. So we have again explicit solution to this, and we can find proper constant that will be valid for the next time step. I know it is very fast, it is very technical, but this is the main strategy for integration. Use a regular ODE solver on the main modes with some influence from the tail, and then use differential inequality on the tail to compute bound for the tail. This algorithm also integrates simultaneously all Galerkin projects and finite dimensional approximations to our system. Okay, how about variational equations? This is the new part, and I'm going to start from ODEs, finite dimensional ODEs. So if we have an ODE, then we can also integrate associative variational equations to the system. And usually our initial conditions are x of 0 belongs to some set x, and v of 0 belongs to some set of matrices v. Quite often it is just identity, but it is not necessary. And this system is non-autonomous and linear. So that means that if we want to compute trajectory, well, solutions to the system at time t plus h, it's sufficient to multiply those two matrices, okay? So it's sufficient to bound solutions to variational equations for just one step and then multiplied by the previous result. From this property, the system is linear. And I would like to also emphasize that for ODEs, the algorithm which can integrate C1 information is not that costly, because actually we are using C1 information to reduce wrapping effect in C0 algorithm. So in order to compute the trajectory of the system after time h, we usually use mean value form to reduce wrapping effect. And here we compute derivative of the numerical method here, okay? In order to construct C1 algorithm, it's sufficient to compute remainder of this for this numerical scheme, for this derivative of numerical scheme. And this is our additional cost. We have to compute rough enclosure for variational part, and we have to compute remainder for this numerical, for this derivative of numerical scheme. This is for finite dimensional ODEs. Same strategies for finding enclosures. We can use either first order enclosure or hierarchy enclosure and check inclusions. So this is just straightforward. If we have C0 algorithms, then we can adopt them to C1 settings. And we would like to do that for now for infinite dimensional systems. We have the next property of our variational equations. Actually, each column of the solution solves the same equation, but with different initial condition. So we have zeros and somewhere one, okay, usually, if the initial condition is identical. So each column is totally independent, okay? So what we can do, okay, how it looks for Kuramoto-Sivashinsky PDE. This is the main system, okay? And here is the system for variational equations. And I would like to emphasize that it has the same structure. So we have strong dissipation here and some nonlinearity. So it has the same properties actually than the original system. So what we can do, we can split our infinite dimensional matrix into finite number of columns and some infinite dimensional block, okay? This red part is x is finite dimensional, so we can integrate this finite number of columns by the same algorithm as I described already, because the system is very similar, okay? The special care should be taken about this infinite dimensional block, Vxy and Vyy. We want to compute norms of those blocks. We cannot compute them explicitly, but we can compute norms of them. So I'm going to describe how we can do that. We are using the notion of logarithmic norms, okay? This is known, what I recall it, given operator norm, we can associate to it a logarithmic norm of a matrix by this expression. And this expression is, this logarithmic norm is easily computable. Here are explicit formulas for well-known operator norms. Well, and the most important property of this logarithmic norm is that it bounds solutions to linear systems. And also it is not a norm, it can be negative. And this is also very profitable. So if this norm is negative, logarithmic norm is negative, then we have, it is somehow optimal bound for the solutions or to linear systems. This logarithmic norm is, goes here to this bound, can be negative. And here we have our main tool for integration of this variational equations for PDEs. Assume that we have just 2 by 2 system. Yes, no, actually not. It can be arbitrary. We have linear non-autonomous linear system, and here are some quantities that satisfy this four inequalities. So we can bound logarithmic norms of those four blocks, and these are just bounds for the vector field. This is what I would like to emphasize. We don't need any enclosure here. This is just a bound for the vector field. So we can compute logarithmic norm of the diagonal blocks. This is alpha and beta and delta, sorry, and regular norms of diagonal blocks. And if those two b and gamma are non-zero, then we can compute explicit numbers lambda 1, lambda 2, and norms of the solutions to the system of those two blocks, Vxy and Vyy, satisfy these inequalities. These are explicitly computable numbers. This is very technical, but very easy to prove, actually. Consider 2 by 2 linear system. It has explicit solution, and with initial condition identity, and then our bounds from the previous slide correspond to the bounds for this explicit solution. Okay, more or less, this is how it goes. And we are going to apply this to infinite dimensional settings. Okay, maybe I will skip this part. It's not that important. Here is a very important part. In order to propagate norms, because we cannot compute expressions for this, we have bounds for norms. In order to propagate those norms, we have several strategies for this. The first strategy is to bound norms for Vxy and Vyy from the entire trajectory. If you remember, we have to compute alpha, beta, gamma, and delta, which is the bound for the vector field only. So we can first integrate C0 algorithm, using C0 algorithm, entire trajectory. Given an enclosure for the entire trajectory, we can compute those quantities of the vector field over this huge set, and then try to apply. This is the less costly approach, okay? But usually gives the worst estimations. The second is to use direct composition. That means given a time step, we can compute those alpha, beta, gamma, delta over each time step and then multiply norms in proper order. I call this direct composition, and this can be done in this way. Okay, so the norm after time t plus h of this xy block, which is the most difficult part actually, can be bounded by this sum of products. Okay. And the most powerful method is a waterfall. Of course, it gives us the best numbers, but it's very costly, actually. I will show you the numbers later. What is the difference? The difference is that here we have multiplication by the norm of Vxx from time ti to time tn. And we allow the dynamics to help us. If we do multiplication by one-step matrix, we multiply norms of matrices, which are often bigger than one, and we have exponential growth of quantities, okay, of numbers. Here we allow the dynamics to work. So if we have rotation, we allow the rotation for a long time, and then we compute a norm of this, okay. And the last strategy is mixed strategy, because waterfall is costly. So we can specify the maximal number of maximal length of waterfall, and say in practice 500, 1000, okay, something like this. And we do mixed strategy, direct composition, and this waterfall. Here is how a waterfall works. Actually, we have an initial condition. Look at the column of matrix, okay? We have zeros and one somewhere, okay? So we start from this kind of initial condition. After one step, it produces x and y. So we split them, okay? And again, we have 0 and y, some different y, and x 0. And then we propagate them separately. And again, the new point contains x non-zero x value and y, we can split them and propagate separately. Okay, so this is how it works more or less. And at the end, we have this bound. And here is some comparison. Okay, this is not for PDE, this is for ODE still, but just to have some feeling, okay? If I remember well, it is for some Galerkin projection for Kuramoto-Sivashinsky PDE. And here we are using C1HO algorithm, which I propose, which is proposed in my work with Irmina Walawska. So this is the best algorithm we have already, okay? And it does not use all these logarithmic terms, etc. So using this algorithm, we have bounds for, Vxy like here, and for Vyy like that. And using bounds for entire trajectory, the worst approach, we obtain these bounds using direct composition, which is a little bit better, but waterfall produces the best numbers. Of course, this is the goal we would like to achieve, but it is impossible. And playing with order of the method and tolerances, we obtain different results, but still waterfall is the best one. Okay, so now I would like to show you how it works for PDE. The first case study was to reproduce a result from 2004 by Wilczak. He proved the existence of, say, stable periodic orbit by means of topological methods. So he was able to obtain the existence of orbit, but the convergence was not proved, okay? On this picture, you see the projection of Poincaré map onto two main modes, A2 and A3. A1 is the Poincaré section, A1 equal to 0. So the rectangle is mapped into itself, more or less. Okay, and this is the image of this rectangle. So we see that it should be attracting periodic orbit inside. And using just topological methods, we can prove the existence of this periodic point. We start from our infinite dimensional set of this form. So we have a box around approximate orbit of this size and geometric tail at the end. And after we compute Poincaré map, we obtain the following quantities, okay? On the first coordinate, we have -5 something to 5 something times 10 to -6, which is less than this, okay? And I would like to emphasize also that this is only slightly larger than eigenvalue, approximate eigenvalue. So our C0 algorithm keeps the shape, okay? On the second coordinate, the eigenvalue is 0.09, but the bound is 9.8 times 10 to -7. So only a little bit larger. And then, of course, eigenvalues are also just randomly computed.
It should be said that those are more or less eigenvector directions, right?
Yes, it is in eigenvector directions, of course. So the set is properly aligned at the beginning. Okay, in proper coordinate system. And here is the result for C1 computation. We computed derivative on this set, and here are eigenvalues on the main block. Well, these are not eigenvalues of the infinite dimensional matrix. These are eigenvalues of the block only, okay? And norms of those infinite dimensional blocks. So from this, we can conclude that this is attracting, more or less, okay? And by the method of computations of eigenvalues, we also obtained that this is a norm. This is the same number. Norm is bounded by the eigenvalue because we are using something like Jagiellonian theorem, so to bound eigenvalues. That was the case study. And at the end, we applied also this to the blue orbit, okay? Because we want to obtain homoclinics to the blue one. And for covering relations, we have these numbers. Because it is unstable, so we have no inclusion on in the first row, but we have covering. And it does not fit that well eigenvalues actually, but still the numbers are controlled. We have inclusion on the all modes except the first one, of course, because there we have expansion. But if we compute the condition is, we have to check that this matrix is positive definite. And we choose Q, this quadratic form, to be of that form, with Q finite dimensional diagonal matrix like that. And if we look at this product, we see that the most dominating parts are the red parts. So this is what happens in the diagonal part. Here we have identity, and those black quantities are just zero because of the numbers here. Okay. Eigenvalues of this finite dimensional block are here. So they are positive, and from those quantities, it is pretty clear that this matrix, infinite dimensional matrix, is positive definite. So the condition is satisfied. Yes, I have something about automatic differentiation for PDE, but I am out of time, I guess, so it's not possible to speak about this. The details are given in our article, and at the very end, I would like to say that these algorithms are implemented in CAPD in quite general form. That is, all vector field dependent things are implemented in some abstract class. So we can inherit from this class and specify the problem dependent things in this class. Solver is abstract, Poincare map is abstract, sets that represent subset of L2 are abstract, etc. So they are implemented in general form. And in this vector field, we have to specify how we compute, how we enlarge the tail to obtain inclusion, or how we evaluate the vector field, how we compute logarithmic norm of the vector field, etc. Yes, it was very fast, but I would like to present a lot of results, starting from the main result and then going deeper into details. So thank you for your attention, and thank you, JB and Jean-Philippe, for the invitation to this seminar.
Thank you very much, Daniel. Fantastic result, I must say, a repeat, and great talk as well. Are there any, let's open the floor for questions. So if you have a question, just unmute yourself and go ahead, I guess.
No questions.
No, okay, so but at least let me start then. So, you showed that there's chaos, but is there any way to somehow get a lower bound on the entropy?
Yes, we can derive lower bound for the entropy, but I have no number. So actually, we have the matrix of symbolic dynamics. So from eigenvalue, we can compute the entropy, but I didn't compute it.
Okay.
But the matrix is explicit, so I know this matrix. So we can extract it, this information. And just to tell you, to jump from one orbit of period 1 to period 2 orbit, we need like 26 or 7 iterations. So this will be matrix with a lot of zeros inside.
Okay,
so the entropy is not very large, and the sets are also very small. So we need a lot of iterations to jump from one set to the other set, because they are of size 10 to minus 6 or something like that.
Mm-hmm.
So a lot of iterations are very close to the original point, and then we jump. But it can be computed.
Okay, nice. Well, I think there was some other question in the chat, but I think Piotr already
answered.
Beat you to answering it. Yeah. So.
Where is chat? Where is chat? I cannot see chat.
It was about whether it was a topological or a measure entropy, but Piotr answered, I think. Are there any other questions for our speaker?
So maybe I will make one comment. If Daniel will go to those conditions C1 or C2.
Yes. Oh, okay. I can switch to.
Okay,
Yes.
okay. So one may ask for which equation C2 is valid. If you look at those conditions, so really there is also conditions that P is bigger than R, which is listed above, which is a part of conditions C2 and C1 in a sense. This complements the thing, okay? And this now this R for Kuramoto-Sivashinsky turns out to be what, Daniel?
P is equal to 4, but R is equal to 2, I guess.
Yes, but then and this R is more or less combination. It takes into account how many derivatives do we lose in this PDE, plus the degree -1, more or less, degree of the polynomial. Okay, so it's not really. I think it should. The condition should be better. Okay, because it turns out that for burgers, C2 does not hold, for example. Okay. But this is the result of the sets we chosen. We chosen the set which is just geometric decay. Okay, if we will put polynomial in the denominator, okay, with geometric decay and k2s in the denominator, then it should be that this condition which guarantees isolation is valid if only this polynomial which enters n has less derivative than in this, let's say, Laplacian part, okay? But in a sense, I mean, this kind of strange condition C2 comes from the shape of sets we are using, okay? Because there is this various algorithms, and then we would like to have them working for all possible PDEs, right? So it's not always the case with various algorithms, okay? And what Daniel presented, it will try, for example, burgers with in 1D burgers, right? Viscous burgers.
Well, we have a lot of strategies for the choice of the tail, of the representation of the tail. Yes, we can use either polynomial or geometric or mixed polybounds. So this is polylogarithmic functions, yes, etc. So there are many strategies for this, and we have to experiment to decide which is the best.
But my point is that the particular form of C2 is not really
important.
Essential, okay, what is essential is that at the end we have this dissipative part dominating that part, okay?
Yes.
Okay.
How you choose cells and decay, etc. It depends, and then you get some particular expression. But what was essential? This was that for high modes, we choose such sets that on the boundary we have entry.
I think there might be another question, but Xufeng, do you still want to? Do you still have a question? I think you.
I have very bad speakers in my laptop, so I can't hear you, actually.
Daniel, there is in chat. Can you see in chat the question?
Yes, you can add CAPD library to online computing platform. Yes, why not? It is open source, and the library is to download from the webpage of the project here.
Yes, just a comment. In my talk, I mentioned to set up an online computing form that everybody can easily share the code and run the code. So I know little about your library, but I would like to try and to install on the platform that everybody can use it easily to run the demo code and share the code based on your library.
Well, the library is under license GPL, so you can use, share, and modify.
Thank you very much.
Under the same license.
Of course, this is just a platform. You can try to access that site, content.online, and to see what kind of
yes,
site
I've
it is.
heard about this platform, and we can try to compile the library first at this platform. Yes, yes, definitely.
Okay, thank you.
The requirements are that C++ say 14 should be supported, and actually we use no other external libraries, just compiler, etc. That's it.
Okay.
Well, for multi-precision, we also require MPFR to be available, but it is not necessary.
So Gandhi is just a virtual machine. So we customize some image, and then later, any other people can start a new machine. So with the customized computing environment, for example, with the CPD inside.
And
well, I didn't get the question actually. Sorry. So sorry for my speakers. I can't hear you actually. Piotr, can you translate the question?
No, I'm not sure. It was kind of.
Did you have another question, Piotr, or?
Yeah, maybe I missed this, but I always ask that question. So how big were the computations? No.
How long the computations are?
Yeah, how long, how big, I don't know.
Okay, for topological part, it was like 240 minutes on 128 cores.
Okay, pretty big.
And 1 terabyte of RAM, but I didn't use it at all. But for C1 computation, well, the longest trajectory, the worst estimations, definitely. So just for period 1, it was like 1 day on the same machine for this blue orbit. And why? This is the reason why we have no heteroclinic orbits, because for the heteroclinic orbit, we need second iteration of Poincare map, and this is the matter of CPU time only. The expected time is 2 months. So I decided to put intermediate sections, but I have some time to experiment with this. So one intermediate section should reduce the time of computations to 2 days. Okay, because this will be composition of two times 1 day. Okay.
But when you say day, you mean on this 140 processors?
Yes, yes, but yes.
Okay.
Because we have to split initial condition to many boxes, and having this number of CPUs, I don't care actually. I split. Otherwise, I will think.
So in 2 months you will have the in 2 months you will have the heteroclinic then, if you don't put any more effort in.
Could you repeat, please?
So in 2 months you will have the heteroclinic then.
Well, 2 months of computations on this machine without extra effort, but maybe my effort will be longer than 2 months. Okay?
Exactly. Yeah, your effort might be longer, right? Might
Yes.
be more. Your effort might be more expensive than the computing time. So.
This is why I am running now. Okay.
Okay.
I'm going to wait 2 months, maybe.
Yeah,
if it don't succeed, then I will think.
Okay. Are there any other questions?
Yes, I have one.
Yes. Thank you.
So you proved the existence of chaos at 0.1212, but is it the parameter that I think in my experience this is a parameter value where we do not observe it numerically? Is it something like it's like unstable chaos in the sense that we don't see it numerically, but it's there?
I didn't make any experiments. I just started to find some horseshoe for this particular parameter, which is just after the cascade of period doublings. So I don't know.
Daniel, so can you show the picture? You know, you have picture of attractor and.
Yes, it looks like Rosler system of Hanon. I mean, yes.
Okay, so
for this particular value, we have this shape of attractor, but this is projection onto 2 variables only. Looks like Hanon models.
Daniel, okay, so let me comment on that, okay? So there's a sequence of period doublings going on, okay? When you decrease this mu parameter, okay? Because for higher values of parameter, you have like fixed point and some other fixed points were born, and some moment some Hof is happening, okay? The attractor is kind of quite simple, okay? And then there is a sequence of period doublings, okay? And then you see, and when you look at that thing, you see that attractor in terms of coordinates, it's quite small thing, okay? But it's, if you kind of run various initial conditions, you will see that, because this is not like ultimate fate of every orbit, okay? There is much more in the invariant set than just this, okay? But if you continue along some periodic orbit which then doubles, you will see that attractor. So in that sense, it's kind of stable, I mean. But you have to know where to look for it, okay? It's not like a big chunk of the phase space, okay?
Okay. Yeah, because I remember doing initial conditions and running chaos. I mean, running simulations at these, that parameter values at this in this range, and I was not observing. It's really much smaller nu that you really see the.
Yes, yes.
Well, the object is very small. Yes, you can look at the values of A1, A2, and A3, and they vary in the very limited range.
Okay.
Yeah, I was wondering if it was a little bit similar to your result. We talked about your result in Michelson or the Kuramoto-Sivashinsky PDE at the beginning of the talk, and I remember also looking at the parameter that you chose there, and it's also kind of it looked unstable, right? You prove chaos, but it's if you numerically integrate the equation, I remember for this ODE, then everything was kind of flying off to infinity. I mean, I guess
yes.
you really have to know where to look. So I was wondering if it was something similar here.
Well, I got some numbers from Piotr, and I just tried to find, say, the trapping region and absorbing domain.
I see.
For this system. So for those numbers, it was just showing me the attractor, the existence of attractor.
So in essence, if you take this rectangle in these two coordinates and some, tail in others, okay, if you iterate it forward, you will see that attractor which is plotted here. This looks like Nonlinear, okay?
Well, this is how the picture was computed. I have chosen one point on the Poincare section from this rectangle and plot just forward iterations, as usually we do. And this is the picture.
It's a small rectangle, right?
Yes, it is very small rectangle, yes.
Yes,
so you have to choose your initial data there by accident to see it. Yeah.
So in fact, Citanovic mentioned a book of his, right, during the talk chat, okay? And there was a paper by Citanovic on periodic orbits for Kuramoto-Sivashinsky, constructing symbolic dynamics, etc., right? And that was for much smaller mu, and that attractor chaotic thing was really large, okay?
Yeah.
But then it will require, from our point of view, higher Galerkin projections, etc., and bigger sets. So likely we will not be able to, I don't know, we will have to cut in more pieces or whatever. So we look into something which will be as small as possible, but still displaying the behavior.
Let me comment also. The sets were so small that we need no subdivision to obtain covering relations at all. So for covering relations, we need three inequalities more or less, to the left, to the right, and across. And I need no subdivision for this because of the size of sets. Of course, this requires also sophisticated algorithm for computations of Poincare map because we represent the result in the coordinate system of the set we are going to cover. Okay, so this is not that straightforward. But for C1, I need to subdivide.
In principle, so with this strategy of really taking small sets, okay, so if the attractor will be large or not, so it should be no difference for us really. But if you would like to see, we will have big horseshoe, okay, on large set, okay, so then this will kill us, okay. But if we will have that strategy like here, so we just follow heteroclinic, in fact, okay. So I mean, so it shouldn't be a problem. I mean, it shouldn't be kind of qualitative problem or even quantitative problem right now, okay. But if you would like to have big horseshoe, okay, so good estimate for lower bound for topological entropy, so then it's better for us that the horseshoe will be on some small set. Okay.
Okay.